Welcome to Nightoria. It's lovely to have you here tonight. Wherever you are right now, whatever the hour reads on the clock beside you, I'm glad you found your way to this quiet corner of the night. Maybe you're under a heavy blanket with the lamp still glowing soft and gold in the corner. Maybe you're on a couch with the rest of the house finally gone still, or on a late train watching the dark slide past the window, or simply lying flat in the dark, waiting for sleep to come and find you. Wherever you are, settle in, let your shoulders drop a little. There's nothing you need to do here except listen, and even that you don't have to do very carefully. And before we begin, if you enjoy these slow journeys through the night and you'd like more of them, a gentle like and a subscribe really do help this sleepy little channel keep going. Small creators like me genuinely rely on it, and it means more than you'd think to everyone already subscribed sitting here with me again tonight. Thank you, truly. And while you're drifting off, I'd love to know one small thing. Where in the world are you watching from tonight, and what time is it in your corner of the dark? Leave it in a comment if you feel like it. I read them, and there's something lovely about imagining all of you scattered across the planet, all listening at once. Now, I'll make my usual promise. I'll try very hard not to make tonight so interesting that it keeps you awake. But if it does, well, at least you'll have learned something beautiful before the sun comes up. That's a fair trade, I think. And here's the real promise, the one that matters. We are going to move slowly tonight. There is no rush. If you drift off before we reach the end, that's perfectly fine. The ideas will still be here, exactly where we left them, whenever you come back. You don't have to grasp every piece. You don't have to follow every thread. Let the words wash over you like warm water, and let the rest take care of itself. So, let me tell you about a photograph. In April of 2019, a team of scientists from all over the world did something nobody had ever managed before. They took a picture of a black hole. And I want you to really sit with how strange that sentence is, because a black hole is almost by definition a thing you cannot see. It's a region of space where gravity has become so impossibly strong that nothing escapes it. Not a spaceship, not a beam of light, nothing. It is the darkest dark there is. Photographing a black hole sounds a little like photographing a shadow or trying to take a picture of silence. And yet there it was. The very first image of a black hole that human eyes had ever seen. To make it, they didn't use one telescope. They used many radio telescopes scattered across the entire Earth, from Hawaii to Spain to the South Pole. All of them pointed at the same tiny patch of sky at the same moment, all of them stitched together by careful timing into one enormous instrument. Together they formed something called the Event Horizon Telescope. And the clever part, the almost unbelievable part, is that by linking telescopes that far apart, they effectively built a single telescope nearly the size of the whole planet. You'd need an eye that big to see something so far away and so small. So they made one out of the Earth itself, and what they pointed it at was a black hole with a name. It's called M87 star, M87 star. The name comes from the galaxy it lives in, a galaxy called Messier 87, an enormous swirl of stars sitting about 55 million light-years away from us. I want to let that distance just hang in the air for a moment, because it's almost too large to hold. A light-year is the distance light travels in a single year, and light is the fastest thing there is. It could circle our entire planet 7 times in 1 second. 55 million of those years stacked end to end. The light that formed this photograph left that black hole when the dinosaurs had only recently vanished from the Earth, and it has been traveling quietly across the emptiness ever since, only to land at last in the dishes of a few radio telescopes on a small blue world on an ordinary spring day. That's how far away this thing is. And it is not a small thing. M87 star is what we call a supermassive black hole, and the supermassive is doing a lot of work in that word. It weighs about 6.5 billion times as much as our Sun, not 6.5 times, 6.5 billion. If you tried to pour our Sun into it, one sun at a time, you'd be pouring for a very, very long while. It is one of the largest things of its kind that we know of anywhere. So that was their subject, a monster. 6.5 billion suns of crushed down gravity, 55 million light-years away, in the heart of another galaxy. And here is the thing I really want you to picture tonight, the thing that the whole rest of our journey is going to grow out of. When that first image finally appeared on their screens, when, after years of work, the picture resolved into something they could actually look at, it was not a black dot. It was not just an absence, a hole, a nothing. What they saw was a ring. A bright, glowing, slightly lopsided ring of orange light, like a smoke ring lit from within, like a wedding band held up to a candle flame. And in the middle of that ring of light, a dark, round, empty space, a shadow, a glowing ring with a dark hole punched through the center. That dark center has a name too. They call it the shadow of the black hole. It's the region where the black hole's gravity is so fierce that any light heading our way gets swallowed before it can reach us. So that patch of the sky simply goes dark. And it is, if I can put it this way, an almost perfectly sized darkness. Across the whole sky, that shadow spans only about 42 micro-arc seconds. I won't trouble you with what a micro-arc second is, except to say it is a unit for measuring impossibly tiny angles, and 42 of them is about the size of a single orange placed on the surface of the moon, seen from a back garden here on Earth. That's the scale of precision we're talking about. They photographed an orange on the moon, made of darkness 55 million light-years away. But it's the glowing ring around that darkness that I want us to fall in love with tonight. Because that ring is not a ring at all, not really. It's a disk. It's a vast, flat, spinning whirlpool of superheated matter, wheeling around the black hole at tremendous speed, glowing white-hot and orange from the sheer violence of its own motion. We see it as a ring only because we're looking at a flat, spinning plate, roughly edge-on, the way a dinner plate seen from the side looks like a glowing line. What's actually there is a disk, a flat, turning, luminous disk of doomed matter, circling the drain of the universe. And there's one more detail in that photograph, a small thing, that turns out to be a kind of secret signature. The ring isn't evenly bright all the way around. One side of it, the bottom side, in the famous image, glows noticeably brighter than the other. About 40% brighter, in fact. And that brightness is not random. It's a clue. It's the disk telling us which way it's spinning. Here's why. The matter in that disk is moving so fast, a meaningful fraction of the speed of light, that the universe's own rules begin to bend the light it gives off. On one side of the disk, the glowing matter is rushing toward us. On the other side, it's rushing away. And when something that bright moves toward you that quickly, its light gets concentrated and intensified, brightened, almost beamed in your direction, like the difference between a siren coming closer and a siren fading away. The side spinning toward us shines brighter. The side spinning away dims down. Scientists call this relativistic Doppler beaming, which is a grand mouthful for a simple idea. The approaching side is brighter. But the point is this. We can look at that photograph, and from the lopsidedness of the glow alone, we can tell you which way the whole enormous disk is turning. We caught it mid-spin. The first picture of a black hole is, when you really look at it, a photograph of a spinning disk frozen in the act of spinning, with the direction of its spin written right there in the light. And now we arrive at the question that's going to carry us gently through the rest of the night: the disk. Because once you start noticing disks, you cannot stop. That same flat spinning shape, it's everywhere. It's around black holes, yes, as we've just seen. But it's also the shape of a newborn solar system, a young star surrounded by a flat platter of gas and dust that will one day become planets. It's the shape of Saturn's rings, that astonishingly thin, wide, glittering sheet of ice circling the planet. It's the shape of our own solar system, with all the planets laid out on nearly the same flat plane, like marbles on a tabletop. And it's the shape of entire galaxies. Our own Milky Way is a vast, flattened disk of hundreds of billions of stars, turning slowly in the dark. So here is the real mystery, the thing I'd like you to carry with you as you drift. Why? Why this shape, again and again and again? Why does the universe, when it has the whole of three-dimensional space to play with, when it could build a sphere, a cube, a cloud, a tangle, anything, keep coming back at every scale imaginable, from rings of ice 10 meters thick to galaxies 100,000 light-years wide, to this one particular shape, the flat, spinning disk? Is it a coincidence? 4 different stories that just happen to rhyme? Or is there one single thread, one quiet rule, running underneath all of them, connecting a glowing ring of fire around a 6 billion sun black hole to the cold, pale rings of Saturn, to the dust that became the ground beneath your feet? There's one rule, and it's a beautiful one. And by the end of tonight, you'll be able to look at the black hole photograph and a picture of Saturn and a spiral galaxy and see the very same law written across all 3. That's the promise. One law, one shape, 20-something orders of magnitude apart, and the same explanation for every single one. And tucked inside it, a second little gift, because once you understand why the disk forms, you'll also understand the strangest twin to the disk, the great jets of matter that black holes fire out of their poles at almost the speed of light. But we'll come to that, no rush, we have all night. So let's begin, slowly, with the thing almost everyone gets a little bit wrong. If you ask most people why matter forms a disk around a black hole, they'll say something like this: gravity pulls everything inward, and as it falls, it starts to spin, and spinning things flatten out so you get a disk. And that's not wrong exactly, but it skips right over the most interesting part. And in skipping it, it misses the whole secret. Because here's the thing that should bother you, the thing that should keep you just slightly awake. Gravity doesn't pull in a flat, disk-like way. Gravity pulls in every direction equally. It pulls up and down just as hard as it pulls side to side. Gravity has no preferred direction at all. It is the most even-handed force there is. So think about what that should mean. If you have a cloud of gas in space and the only thing acting on it is gravity pulling every speck toward the center from every direction equally, what shape should it collapse into? Not a disk, a sphere, a ball. Gravity, left entirely to itself, makes spheres. That's why stars are round, that's why planets are round, that's why the sun and the moon and the earth are all, more or less, balls. Pure gravity wants a point at the center and a sphere around it. It does not ever, on its own, want a flat plate. So the disk is a genuine puzzle. If gravity makes spheres, then the disk is not what gravity wants. The disk is something getting in gravity's way, and here I think is the single loveliest way to say it, the sentence I'd like you to fall asleep holding. A disk is not what falling looks like. A disk is what not being able to fall looks like. Let me say that again, slower, because it really is the heart of everything. The disk is not the shape of matter falling in. The disk is the shape of matter that desperately wants to fall in. and isn't allowed to. The disk is a compromise, a truce, the shape of I'm trying to fall and something won't let me. And the something that won't let it is one of the deepest, most stubborn rules in all of physics. It's called the conservation of angular momentum, and I promise I'm going to make it gentle. You already know it in your body, even if you've never named it. You've seen a figure skater spinning on the ice, arms stretched out wide, turning slowly, and then she pulls her arms in tight against her chest, and suddenly she's spinning fast, a blur, faster and faster, just from tucking her arms in. Nobody pushed her, no one gave her a shove. She sped up all on her own simply by getting smaller. That's it. That's the whole rule, right there in your mind's eye. That's angular momentum being conserved. The idea is this: anything that's spinning has a certain amount of spin, and the universe is extraordinarily insistent that this spin be kept. It can be passed around, handed from one thing to another, but it cannot simply vanish. Now, the amount of spin a thing has depends on three things: how heavy it is, how fast it's turning, and, crucially, how far out from the center the spinning stuff is. Physicists write it in a tidy little formula, L equals mvr, where the L is that quantity of spin and the r is that distance from the center. And the rule is that L stays the same. So if the distance, the r, shrinks, if the spinning material moves inward, closer to the center, then to keep that L from changing, the speed has to climb. The smaller the circle, the faster the spin. The skater pulls her arms in, the r gets smaller, so the speed leaps up. She can't help it. The universe is balancing its books, and this isn't just a handy rule of thumb, it runs astonishingly deep. There's a beautiful piece of mathematics discovered by Emmy Noether that says conservation of angular momentum is tied directly to a simple fact about space itself, the fact that space looks the same no matter which way you turn to face it. There's no special direction in the universe, no cosmic up. And out of that plain, almost obvious symmetry, the whole law of conserved spin falls out, ironclad. That's Noether's theorem, and it's one of the most profound ideas in physics, and tonight, all you need to take from it is this: the universe guards its spin fiercely, and that fierceness is woven into the very fabric of space. You cannot cheat it. So now hold the skater in one hand and the collapsing cloud of gas in the other, and watch what happens when they meet. Picture an enormous cloud of gas and dust drifting in space, far from anything, and picture that this cloud, like very nearly everything in the universe, has a tiny bit of overall spin to it, just a gentle, lazy turning, almost too slow to notice. Now let gravity start to pull it together. The cloud begins to shrink, every part falling toward the center. And here is where the disk is born. Watch the two different directions because they behave completely differently. First, think about a speck of gas sitting up near the top of the cloud, near what we might call the North Pole, directly above the center. Along the axis, the whole thing is spinning around. That speck can fall straight down toward the center with nothing in its way. Its spinning, its circling motion doesn't carry it sideways here. It's right on the axis. So gravity just pulls it down freely, and in it comes. The poles collapse. The top and bottom of the cloud cave straight inward. No resistance, no problem. The cloud gets flatter and flatter from above and below, squashed like a marshmallow pressed between two hands. But now, think about a speck of gas out at the side, out at the equator, the widest part of the cloud, the part that's whipping around as the whole thing spins. As that speck tries to fall inward toward the center, its distance from the center shrinks. And we know what the rule demands. As r shrinks, the speed must rise. So the closer it tries to fall, the faster it's forced to circle, faster and faster, just like the skater pulling in her arms. And very quickly it's circling so fast that it simply swings right past the center and back out the other side like a stone whirled on a string, like water flung to the rim of a spinning bucket. It cannot fall in. Every time it tries, its own conserved spin flings it back out into orbit. There's an invisible wall here, a wall made not of any substance but purely of motion and conservation, and physicists call it the centrifugal barrier. At the equator, that barrier holds the matter up. It cannot get to the center. It's forbidden. So look at what you've got. Top and bottom, the poles, collapse freely all the way in. The sides, the equator, cannot collapse at all, held out by the barrier of their own spin. The cloud gets crushed, flat from above and below, while staying spread wide around the middle, squashed vertically, propped open horizontally. And what shape is that? Thin in one direction, broad in the other, turning as it goes. A disk. That's it. That is the whole secret of why the universe loves this shape. It isn't that gravity wants a disk. Gravity wanted a sphere the whole time. It's that gravity is allowed to win along the poles and forbidden to win along the equator. And a disk is simply the shape of that disagreement. The disk is exactly, precisely, the shape of matter that has fallen as far as it's allowed to fall and no further. It's the frozen compromise between gravity pulling everything to a point and conserved spin, refusing to let the equator go. The disk is what I want to fall but I'm not allowed looks like, made visible, made enormous, made of fire and ice and starlight, written across the whole sky. And now let me give you the gift that falls right out of this, the one that flips a thing you thought you knew completely on its head. Because we all carry around this image of a black hole as a kind of cosmic vacuum cleaner, don't we? An unstoppable drain, sucking in everything around it, gobbling up stars and light and anything foolish enough to drift too close. It's a wonderful, frightening picture. And it's almost entirely wrong. A black hole is, in truth, one of the worst vacuum cleaners in the entire universe. Think about it with everything we've just built. When matter drifts toward a black hole, it almost never falls straight in. It can't. The very same centrifugal barrier we just met stands in its way. The matter has spin, it has angular momentum, and that spin forbids the straight plunge just as surely as it forbade it in our cloud of gas. So instead of falling in, the matter is flung into orbit. It circles and circles and keeps on circling around and around, piling up into, yes, a disk, the very disk that the Event Horizon Telescope photographed glowing around M87's star. Almost nothing that approaches a black hole actually falls in. The overwhelming majority of it just orbits, trapped not by some inescapable suction, but by its own stubborn, conserved spin, refusing to let it drop. A black hole doesn't suck things in. Mostly, it just makes them go around. It's a terrible vacuum cleaner. And that refusal to fall, the endless, forbidden, circling, almost falling, is precisely the thing that builds the great glowing disk in the first place. So now we have our shape, and we have the reason for it. The disk is the truce between gravity and spin. The poles collapse, the equator can't, and the universe builds the same flat whirlpool everywhere it finds something turning and trying to fall. But this leaves us gently with a puzzle, a loose thread to follow as we drift deeper into the night. Because if the matter in that disk really cannot fall in, if its own spin forbids it, holds it out at the barrier, keeps it circling forever, then how does a black hole ever eat at all? How does it grow? How does it glow so fiercely, hot enough to shine across 55 million light years if nothing's actually allowed to fall? Something must be letting a little of that matter slip past the barrier slowly, quietly, against all the rules we've just laid down. Something has to be loosening the truce. And the answer to that, how matter cheats its way past its own conserved spin, and what that cheating has to do with the strange ice rings of Saturn and the ground beneath your feet, is where we'll wander next. But for now, just hold the picture. A ring of fire glowing in the dark 55 million years away. Brighter on the side that's spinning toward us. A dark, quiet shadow at its heart. And all of it, every bit of it, simply the shape of matter that wanted to fall and wasn't allowed. Rest there for a moment. We'll go on slowly. Let me sit with that picture a little longer because it rewards the patience. That bright, lopsided ring of light around a pool of darkness. When the Event Horizon Telescope released it, back in April of 2019, it wasn't really one telescope at all. It was a whole planet's worth of dishes scattered from the deserts to the South Pole, all stitched together to act as a single eye the size of the Earth. And what that eye was staring at sat at the center of a galaxy called Messier 87, M87 for short, a black hole so large it makes our sun look like a grain of sand on a beach that stretches to the horizon. 6.5 billion times the mass of the sun. Try to hold that number gently without straining, not 6.5 million, billion. A single object weighing as much as 6.5 billion of our stars, all folded into a darkness so dense that light itself can't climb back out. And it sits 55 million light-years away. Which means the light in that photograph left M87 around the time the dinosaurs were already long gone, when the world was still settling into something new. It traveled quietly across all that emptiness for 55 million years just to land on our dishes one spring. There's something soft in that, isn't there? You're looking at the deep past. A photograph of a moment older than almost everything you've ever known. The dark patch in the middle has a name. It's called the shadow, and it's tiny from our point of view, about 42 micro-arcseconds across. That's a measurement of angle, of how big a thing looks in the sky, and a micro-arcsecond is almost unimaginably small. Picture trying to spot a single donut sitting on the surface of the moon from your backyard. That's roughly the scale of what the telescope had to resolve, a donut on the moon. And somehow, by binding the whole Earth into one eye, we did it. But the part I want you to keep with you, the part that matters most for tonight, is that the ring isn't evenly bright. One side glows noticeably more fiercely than the other. About 40% brighter. And that lopsidedness isn't a flaw in the image or a smudge or a trick of the camera. It's the spin made visible. The disk is turning and the side that happens to be rotating toward us, racing in our direction at a good fraction of the speed of light, gets brightened by that motion. Light from an approaching source bunches up, intensifies, leans toward us. The physicists call it relativistic Doppler beaming, which is a heavy phrase for a gentle idea. The side coming toward you shines harder than the side going away. Like a runner who seems louder as they sprint past you and quieter as they recede. So that asymmetry in the photo is, quite literally, the universe showing you which way the disk is spinning. The bright side is the side falling toward us. We didn't just photograph a black hole, we photographed which direction it turns. If you're drifting a little now, that's perfectly fine. You don't need to keep the numbers. You don't need to hold the angles. Let them go soft. The ideas will still be here, waiting whenever you come back to them. Tomorrow night or the one after. There's no quiz at the end of this. There never is in Nitoria. You're allowed to simply float on the sound of it. And while you're settling, if these slow journeys through the dark are the kind of thing you want more of, a quiet like and a subscribe genuinely help this sleepy little channel keep going. Small creators like me really do lean on it. It's the whole reason these nights can exist. And to those of you already here, already part of this, already returning night after night, thank you. Truly, I notice So before we wander any further, I'd love to know, where in the world are you watching from tonight? What time is it in your corner of the dark? Leave it down below, and let's see how far across the world this quiet little room reaches. Now, settle back in, because there's a deeper question hiding underneath that photograph, and I want to set it gently in front of you before we go on. We've seen this one disk around this one black hole. But here's the strange thing, that same flat, glowing, spinning shape shows up almost everywhere. The universe builds something around newborn stars, around old dying ones, in the rings of Saturn hanging out there in our own solar system right now. In the great pinwheel of the Milky Way, the galaxy you yourself are sitting inside of tonight, in your bed. The same flat disk, over and over, at scales so different they're almost laughable to compare. Why? Why does the cosmos keep reaching for this one shape? Is it a coincidence? 4 different stories that just happen to rhyme? Or is something deeper going on, one single rule writing itself out again and again, from the rings of a planet to the body of a galaxy? That's the thread we'll follow tonight. And I'll tell you now softly, so you have it to hold, it is not a coincidence. It's one law, one stubborn, beautiful fact about the way spinning things behave, repeating itself across the whole universe. And once you can see it, you'll never look at a galaxy photo or Saturn or that black hole the same way again. So let's begin, slowly, at the heart of it. Here's the piece almost everyone misses. When you imagine a black hole or a forming star, you probably picture gravity simply pulling everything inward, pulling and pulling until it all piles up at a single point. And gravity does want that. Gravity, on its own, with nothing to argue against it, would build a sphere, a neat, round ball of matter collapsing toward the center from every direction equally. No disk at all. So here's the real question, the one underneath everything. If gravity pulls in every direction the same, why isn't the universe just full of spheres? Why a flat disk instead of a round ball? And the answer is that gravity is not arguing with nothing. It's arguing with spin. Almost everything in the universe is turning, even if just a little. A cloud of gas drifting in space has some faint, leftover rotation. And rotation comes with something the physicists call angular momentum, the amount of spin a system carries. You can write it, for a single particle, as a small, tidy expression. L equals m times v times r. The mass, times how fast it's moving, times how far it sits from the center. Don't worry about the letters, just hold the feeling of it. The further out something orbits and the faster it goes, the more spin it's carrying. And here is the crucial, load-bearing fact of this whole night, that spin cannot simply vanish, it's a conserved quantity. In an isolated system, angular momentum can be moved around, handed from one piece to another, shuffled outward or inward, but it can never be destroyed. It can't just leak away into nothing. There's a deep and elegant reason for this. A thread discovered by the mathematician Emmy Noether, who showed that because the laws of physics don't care which way you're facing, because space has no preferred direction, to spin itself must be conserved. The universe's indifference to direction is exactly why rotation is forever. So now we have our 2 characters sitting in tension. Gravity, which wants to pull everything down to a single point, and conserved angular momentum, which absolutely forbids it from getting there. And the shape we see, the disk, is what happens when those 2 stubborn facts are forced to make peace. So here we are, sitting with this elegant conflict. Gravity pulling inward, angular momentum holding its ground. And you might be wondering, if the spin can't disappear, what exactly does happen? How does anything change at all? How does a spinning cloud of gas ever settle into anything? This is where the story gets genuinely beautiful and a little surprising. Think about what a falling cloud of gas is actually doing. In energy terms, it has two kinds of energy in play. It has kinetic energy, the energy of motion, all that spinning and tumbling. And it has potential energy, the stored energy of gravity, the energy locked into the fact that it's hovering at a distance from whatever is pulling it. As it falls inward, some of that potential energy gets released, and it has to go somewhere. Where it goes is heat and light. When the particles in a cloud of gas are packed close enough and moving fast enough, they collide constantly. Billions of tiny collisions happening everywhere inside the gas at once, and those collisions are messy, chaotic, friction on the smallest possible scale. That friction converts the kinetic energy of random motion into heat, and a hot gas radiates. It glows, it shines. It sends that heat energy outward as photons, as electromagnetic waves, as light in all its frequencies, from the gentle warmth of infrared right through to the scorching blaze of X-rays if it gets hot enough. The energy leaves the system. It escapes. So energy can radiate. Energy bleeds out of the cloud as light. That is relatively easy, physically speaking. Light travels at the speed of light and doesn't look back. But angular momentum is a completely different story. Angular momentum is desperately hard to radiate away. Photons carry a tiny amount of spin. They do, technically. But the amount is almost laughably small compared to the angular momentum locked up in a spinning cloud of gas. If a cloud of gas tried to shed its spin by glowing, it would have to glow for an almost unimaginable length of time to get rid of even a fraction of it. The angular momentum is, for practical purposes, stuck, trapped. It has nowhere easy to go. And this asymmetry, this fundamental difference between the fates of energy and angular momentum, is the heart of why disks exist. Not gravity, not spin on its own. The asymmetry between the two. Energy finds the exit. Angular momentum cannot. So picture what happens to a collapsing cloud. It loses energy constantly, radiating it away as heat and light. As it loses energy, it falls toward the lowest energy state it can reach. Lower energy means tighter, more compact, more settled. In the absence of any constraints, it would fall all the way to a point, but it can't reach a point. It's still carrying all that angular momentum, stubbornly conserved, insisting on the spin. The lowest energy state available to a system with a fixed, unchangeable amount of angular momentum is not a point. It's a circle. A circular orbit is the most efficient, most compact, lowest energy way of carrying a given amount of angular momentum. Think of it this way: a particle orbiting in a perfect circle is carrying all its angular momentum in the most economical form possible. It's not wasting energy on any elliptical stretching or oscillation. It's just going around cleanly. That is the minimum. That is the bottom of the energy landscape, given the constraint of the spin. So the cloud, losing energy all the time through radiation, but unable to lose its angular momentum, does the only thing it can do. It falls and settles, not to a point, to a ring. And then, because there are many particles at many different distances and many different inclinations, to a flat, rotating disk. A disk where every particle is spending as little energy as possible while still honoring its spin. The disk is the minimum energy shape for a fixed amount of angular momentum. It is the answer the universe finds when it works out what shape to make something that wants to fall but is carrying spin it cannot shed. The word for this kind of shape in physics is a minimum of the effective potential. The gas literally rolls downhill energetically to the flattest, most circular arrangement it can find. The cloud doesn't choose to become a disk. It doesn't plan it. It collapses, radiates, and the disk is simply what's left when the system has lost as much energy as it's allowed to lose. There's a softness to that idea, I find. The disk isn't imposed from outside, it's arrived at, the universe doing its homework and handing in the neatest answer. Now here's the part that might keep you gently puzzled as you drift. If matter in a disk is carrying all this angular momentum, and angular momentum forbids it from falling inward, then how does anything ever reach the center? How does a black hole eat? How does a protostar gather mass? How does a quasar shine? This is what astrophysicists call the friction problem, and it's sat unresolved for a surprisingly long time. The solution begins with a paper published in 1973. Two researchers, Nikolai Shakura and Rashid Sunyaev, sat down and worked out the mathematics of a disk where some kind of internal friction is at work. They didn't know exactly what the friction was, well, we'll get to that, but they reasoned about what any friction must do in a rotating disk, and the answer they found is deeply elegant. Friction between adjacent layers of gas moving at slightly different speeds acts like a viscosity, like a thick, slow stickiness between the layers. And in a rotating disk, what this viscosity does is couple the faster-moving inner material to the slower-moving outer material. The inner stuff, orbiting faster because it's closer to the center, drags on the outer stuff, transferring some of its spin outward. A little of the angular momentum from the inner region gets handed to the outer region, and here is where the beauty comes in. When the inner material gives up some of its angular momentum, it loses the spin that was holding it up against gravity, and it falls. It spirals inward just a little. It descends to a tighter orbit, losing energy as it goes, radiating that energy as heat. And the outer material, having received extra angular momentum, drifts outward. It's been paid in spin and moves to a wider orbit. So a disk drains from the inside out. Mass spirals inward toward the center, where eventually it might cross the innermost stable orbit around a black hole and fall in. Angular momentum spirals outward, carried by a smaller amount of matter, moving to wider and wider orbits, eventually leaving the system entirely. The disk is not static. It is a slow, continuous drain, mass flowing in toward the center, angular momentum flowing out toward the edge. Shakura and Sunyaev described this beautifully, and their alpha disk model, named for the Greek letter they used to parameterize the unknown viscosity, became one of the most cited papers in all of astrophysics. It is, in a quiet way, one of the great intellectual achievements of the 20th century. But the question they left open was the one that mattered most. What is the friction? Because in a near vacuum and in the thin ionized gas of an accretion disk, ordinary molecular viscosity is essentially nothing. You know the feeling of moving your hand through thick honey, that resistance, that drag? That's viscosity. In dense, ordinary matter, it comes from molecules bumping into each other constantly, transferring momentum through contact. But in an accretion disk, the gas is so thin, so sparse, that molecular collisions are rare. The molecular viscosity of the gas is orders of magnitude too small to produce the friction rates that Shakura and Sunyaev's model required. By many calculations, a disk with only molecular viscosity would drain so slowly that the universe wouldn't be old enough to have produced the accretion rates we actually observe. Something else had to be providing the stickiness, something much more powerful. For nearly 2 decades, this was an open problem. A genuine puzzle. The math worked beautifully, the observations agreed with the models, but the underlying mechanism was a mystery. Physicists knew there had to be an effective viscosity orders of magnitude larger than the molecular kind, but they couldn't say where it was coming from. The answer, when it arrived, was magnetic. In 1991, Stephen Balbus and John Hawley published a paper that solved it. Their insight was about instability, specifically about what happens when a weak magnetic field threads through a differentially rotating disk of plasma. A differentially rotating disk is one where the inner regions orbit faster than the outer ones, which is exactly what happens in any gravitational accretion disk orbiting a central mass. And the key word is weak. The field doesn't have to be strong. A modest, even tiny magnetic field is enough. Here is what they showed. Imagine a thin magnetic field line threading vertically through the disk, connecting a parcel of gas in the inner, faster-moving region with a parcel in the outer, slower-moving region. The magnetic field line is like a very gentle rubber band stretching between two regions orbiting at different speeds. The inner parcel moves faster than the outer one. This stretches the field line, and the stretched field line, because magnetic fields resist being stretched, pulls backward on the inner parcel, slowing it down, and forward on the outer parcel, speeding it up. But remember what we just learned from Shakura and Sunyaev. When the inner material loses angular momentum, it falls inward. When the outer material gains angular momentum, it moves outward. The magnetic field line, in being stretched, has amplified the separation between the two parcels, making the situation more extreme, not less. This is the signature of an instability. The small perturbation makes itself worse. The field line stretches further, transfers more angular momentum, the parcels separate more, the field stretches more, and very quickly the system descends into turbulence. This is the magnetorotational instability, the MRI, and the turbulence it generates acts as an enormously effective viscosity, far larger than molecular viscosity, large enough to explain the accretion rates we actually measure. The magnetic field is not the viscosity itself, it's the mechanism that generates a turbulent chaos which then acts as the viscosity. The MRI converts the orderly differential rotation of the disk into a roiling, churning turbulence, and that turbulence transports angular momentum outward with breathtaking efficiency. Balbus and Hawley's discovery was, in the words of many physicists who studied it, one of those moments where a long-standing embarrassment in a field is suddenly and completely resolved. The question of what friction could possibly power accretion disks had nagged at astrophysics for nearly 20 years, and the answer turned out to be hiding in a subtle instability of magnetized rotating plasma that nobody had thought to look for in quite that way. So now the picture is complete, at least in outline. Gravity draws matter in. Conservation of angular momentum forces it to orbit instead of fall directly. The orbit radiates energy and the gas settles into the lowest energy shape consistent with its spin, a disk. Inside the disk, the magnetorotational instability generates turbulence, which provides an effective viscosity, which transports angular momentum outward, which allows mass to spiral inward. The whole thing is a slow, elegant machine, powered by gravity but regulated by spin, with magnetism providing the hidden gearwork. And as the mass spirals inward and the gas loses energy, something else is happening. Something you can see if you look. It gets hot. The inner regions of an accretion disk are the most extreme environments of temperature in the known universe, at least for ordinary matter, spread out in a structure rather than packed into a neutron star or the center of a collapsing star. As material spirals inward and loses gravitational potential energy, that energy has to go somewhere. Most of it, as we've discussed, radiates away. But the process of radiating is not quiet. The gas is dense enough and turbulent enough that it's constantly colliding, constantly converting kinetic energy into heat and then into radiation. The temperature in a disk rises steeply as you move inward toward the central mass. In a protoplanetary disk around a forming star, the temperatures vary from a few hundred Kelvin in the outer cold regions. Cold enough for ice to exist, cold enough for the complex chemistry that eventually produces the stuff of life, to several thousand Kelvin near the inner edge, hot enough to melt rock. That's the temperature gradient that creates the frost line in a young solar system, the distance inside which water ice vaporizes, inside which rocky planets form, and outside which icy bodies accumulate. The disk's temperature profile is a map of chemistry, but in the disk around a black hole, the scale is entirely different. Near the innermost stable orbit around a stellar mass black hole, which might be just a few kilometers across, temperatures can reach tens of millions of Kelvin. The gas is not just hot, it is blazing with X-rays. It is radiating in frequencies of light that no ordinary gas in any ordinary temperature environment produces. The inner disk of a black hole glows at energies that would be lethal in an instant to any life form anywhere near it. And this heat, this staggering X-ray bright heat, is what the Event Horizon Telescope's image captured, in a way. Not the heat directly, because EHT works in radio waves, not X-rays, but the image shows the glowing ring around MAT Saturn, and that glow is the product of this same process. Gravitational energy, released as matter spirals inward, converted to heat by friction and turbulence, and then radiated outward as electromagnetic radiation at every frequency, including the radio frequencies that EHT can see. The glow in that image is what gravity and friction look like when they're made visible by conservation of energy. Friction made light. That is, in one sense, all that glowing ring is. Now, the temperature gradient does something else besides making the disk bright. It creates a pressure gradient too. Hotter gas has higher pressure, and the inner disk is hot enough and dense enough that this pressure matters. This is part of what sustains the disk against gravity in the vertical direction. The gas has thermal pressure that puffs it up just a little, so the disk isn't infinitely thin. The disk has a thickness, a vertical structure, a kind of atmosphere. The precise shape, how puffed up the disk is relative to its radius, depends on the balance between gravity, pressure, and the disk's own rotation. This is some of the most intricate physics in modern astrophysics, and researchers who model it spend careers running simulations on the largest supercomputers in the world. But perhaps the most striking thing about all this heating, all this radiation, is what it implies about efficiency. How good a machine is the accretion disk? The answer is staggering. When we burn hydrogen in the sun through nuclear fusion, the process that has powered every star that has ever shone, roughly 0.7% of the rest mass energy of the hydrogen is converted into radiation. That means that if you take 1 kilogram of hydrogen and fuse it into helium, you get out about 7 grams worth of energy. Converted to joules by Einstein's famous equation, that's still an enormous amount, but the efficiency is less than 1%. An accretion disk around a black hole does wildly better. For a non-rotating Schwarzschild black hole, the innermost stable circular orbit, the closest point where matter can orbit without falling in, releases roughly 6% of the rest mass energy as radiation before crossing in. 6%. That's already nearly 9 times better than nuclear fusion. But for a maximally spinning Kerr black hole, a black hole rotating as fast as it physically can, the innermost stable orbit is pushed much closer to the horizon and the efficiency rises to somewhere around 32%. A third of the rest mass of infalling matter converted to pure radiation. To feel what that means, if you could take 1 kilogram of anything, a handful of dust, a rock, a cup of water, anything at all, and drop it into an accretion disk around a spinning black hole, you would get back roughly 320 grams worth of energy, as light, as X-rays, as radiation blazing outward across the cosmos. There is no more efficient large-scale energy conversion process known in nature. Nothing competes, not fusion, not fission, not chemistry, not any engine we have ever built or imagined, short of the exotic and theoretical process of matter meeting antimatter and annihilating completely. The accretion disk is the universe's most efficient power plant, and this is why quasars exist. A quasar is, at its core, a supermassive black hole actively accreting, drawing in enormous amounts of gas and dust and star stuff from its surroundings, running it through this disk and converting a significant fraction of its mass into pure light. The most luminous quasars in the universe outshine their host galaxies by factors of hundreds. A single black hole, perhaps a few billion solar masses, surrounded by a disk, can produce more light than 100 billion stars. The stars of the galaxy, all of them together, are outshone by the disk. There are quasars so distant and so bright that we can see them from the far end of the observable universe, their light having traveled for more than 13 billion years to reach us. They are visible from almost any distance because nothing in the universe shines as hard as matter falling, not quite falling, into a black hole. Every photon we receive from a distant quasar is the glow of that machine. The glow of angular momentum refusing to surrender, of energy finding its way out, of the disk as a power station at the heart of a galaxy. The efficiency of the process, that extraordinary 6% to 32% conversion rate, is itself a product of the geometry. The efficiency is highest for a Kerr black hole because the spinning black hole drags space-time along with it in a phenomenon called frame dragging, which pushes the innermost stable orbit closer to the horizon, which means infalling matter gives up more gravitational potential energy before it crosses the point of no return. The spin of the black hole enhances the disk's power output. And we'll come back to that spin because it does something else, something even more dramatic than powering the disk. But for now, settle with this picture. A disk forming from a cloud of gas and spin. Energy radiating away through friction and collision, finding the exit as light and heat. Angular momentum staying stubbornly put, shaping the disk's geometry, determining its thinness and its size. The magneto-rotational instability providing the hidden engine of viscosity that allows mass to slowly, spirally drain inward. The temperature rising toward the center, the innermost regions blazing in X-rays. The whole system acting as an engine of almost incomprehensible efficiency, powering quasars bright enough to illuminate the early universe. And underneath all of it, the conserved spin, the spin that cannot leave, the spin that in refusing to leave built the disk in the first place. I want you to hold that image for a moment. A disk, flat, glowing, hot at the center and cool at the edge, spinning, draining, burning with the light of matter that wanted to fall but couldn't quite do it sideways. There's something that happens when you stare at that image long enough. When you really sit with the idea that the disk is not a coincidence and not a preference, but an inevitability, the only stable solution to a set of constraints, you start to feel it as something almost simple, almost obvious, in the way that all deep things feel once you've understood them. Of course, the universe makes disks. How could it make anything else? But there is a detail hiding at the edge of the picture, a strange, powerful, almost violent detail that we haven't looked at yet. If you look at an accretion disk around a black hole, really look at it, the full three-dimensional picture, you notice that the disk fills the equatorial plane. It extends outward in every direction along the equator, a great flat wheel of glowing gas. The centrifugal barrier holds matter in the equatorial plane. The spin preserves the orbit, but the poles are open. The spin axis, the axis around which everything is rotating, is not blocked by the disk. Matter doesn't pile up there. The centrifugal barrier doesn't operate along the poles, and whatever is happening in the disk, the turbulence, the magnetic fields wound up by the differential rotation, the energy pouring outward, is all concentrated in a specific region. Everywhere in the disk but not along the poles, and something at the poles finds that open channel and uses it. That is the next part of the story. The part that starts with a jet, seen for the first time in 1918, and ends with plasma moving so fast that it appears, impossibly, to be breaking the speed of light. But that is also a story that deserves to be told slowly, and we'll get there. There's no hurry tonight. For now, let the idea of the disk just settle in. The disk as a machine, the disk as a compromise between gravity and spin. The disk as a furnace, burning with the light of matter that found a middle path between falling and staying. The disk as the shape you get when energy finds the exit and angular momentum refuses to follow. It's a genuinely beautiful idea if you let yourself rest with it. The universe, working with just a handful of conservation laws and a little bit of magnetic field, builds the same structure everywhere it's given the right ingredients. Not because it's trying to, not because there's anything guiding the process toward beauty or elegance. Simply because the physics has only one answer to the question. Given spin, given gravity, given a way to radiate energy but not angular momentum, given the slow, turbulent transport that friction provides, the only stable outcome is a disk. And in a universe so vast and so varied, full of phenomena so different in scale and character that they barely seem to belong to the same physical reality, it's a quiet kind of wonder that one set of laws applied again and again produces the same answer, the same shape, every time the same flat wheel of light. And somewhere in the middle of all this machinery, at the very center of the disk where the temperature reaches its maximum and the gravity its most intense, the black hole waits. Not like a vacuum cleaner, as we said, not like a drain that swallows everything, more like a quiet inevitability. Most of the matter that approaches it will orbit for a long time before spiraling slowly in. The disk is far larger than the black hole. The black hole is at the center of an enormous luminous spinning structure that it has created simply by existing. There's something almost small about the black hole set against the disk it generates. The shadow in the Event Horizon Telescope image. That dark region in the center, maybe 42 microarc seconds across in the case of M87 tanks, a measurement so precise it required a telescope the size of the entire Earth, is surrounded by a ring of light that is itself the product of all this process. The shadow is not the black hole, the shadow is the region where light bent by gravity fails to escape, a dark circle carved by geometry. The glowing ring around it is the disk, the friction, the angular momentum machine, all rendered visible in radio waves detected by 8 observatories across the face of the planet. Their data combined by algorithms running on banks of computers, their results released to the world on the 10th of April 2019, the most precise, most difficult observation in the history of astronomy. And what it showed ultimately was a disk. Of course it was a disk. That's what the universe makes when it has spin and gravity and enough time. It makes a disk. And the disk glows because energy always finds the exit, even when angular momentum cannot. The glow is the sound of that asymmetry translated into light. If your eyes are getting heavy now, that's a good thing. Let the image of the glowing disk be the last thing you carry with you for a while. Hot at the center, cool at the edge, spinning, draining, pouring light into the darkness around it. The machine runs on the spin that cannot leave. And in the morning, if you remember nothing else from tonight, remember this. The most efficient engine in the universe is not made of gears or circuits or any technology we have ever built. It's made of gas and magnetic fields and conservation of spin. It's been running in the centers of galaxies since the universe was less than 1 billion years old. And when the Event Horizon Telescope finally took its picture, what we saw was not the darkness at the center, dramatic as that was. What we saw was the glow. That glow tells us everything about how matter behaves when it falls towards something it cannot quite reach. It tells us about energy and angular momentum and the strange, deep geometry that results when those two quantities follow different rules. It tells us about magnetism doing work in a near vacuum, about turbulence carrying spin outward while mass spirals in, about temperature rising to extremes we can barely imagine, and then radiating all of that heat away as light. And yet, even as all of this is happening, even as the disk blazes and drains and spins, there are places in the system where something different is taking place, places where the energy is not radiating gently outward in every direction, places where it is being focused, collimated, squeezed into a narrow beam and fired outward at speeds approaching the fundamental speed limit of the universe itself. The poles are still open, the machine is still running, and what comes out of the poles is not heat, not light, not the gentle glow of friction made visible. It's a jet, and it travels for 5,000 light years. Let's talk about that jet for a moment. Because if the disk is the universe's answer to the question of what happens when matter cannot fall straight in, then the jet is the answer to a different question, one that follows almost immediately, and that is just as important. If angular momentum is the barrier keeping matter from plunging to the center, if the centrifugal force is what holds the equatorial plane open and prevents the collapse to a point, then the poles are different. The poles, by definition, are the one place where none of that applies. There is no centrifugal barrier along the rotation axis. Nothing is spinning away from the center up there. Nothing is held up by its own orbital momentum. The spin axis is the one direction in the entire system that is genuinely completely open, and nature, as it turns out, is very good at finding open doors. The material that has given up its angular momentum, the gas that the magneto-rotational instability has slowly, patiently stripped of its spin, passing it outward to neighboring rings of the disk while letting the inner layers fall, that material does eventually cross the last barrier and spiral inward. But not everything that approaches the black hole ends up crossing the event horizon. And not everything that crosses the disk ends up going down. Some of what the accretion system produces is ejected, not absorbed. Some of the energy that the system generates is not radiated quietly away as X-rays and infrared light from a glowing ring. Some of it is channeled, shaped, accelerated, and launched outward along the polar axis at a speed that is, depending on the system and the moment and the particular jet in question, something like 99.9% of the speed of light. Not 99%, 99.9. Take a moment with that number if you like, there's no rush. The jet has been traveling for a very long time already. The jet coming from the black hole at the center of the galaxy Messier 87, the same black hole that the Event Horizon Telescope photographed in April of 2019, the same M87 star that we described earlier as sitting about 55 million light-years away and massing around 6.5 billion times the Sun. That jet has been known to science since 1918. The astronomer Heber Curtis, working at Lick Observatory, noticed a curious feature in photographs of Messier 87. A faint line, almost like a scratch on the image, extending outward from the galaxy's core. He described it, in the language of the time, as a curious straight ray. He had no way of knowing what it was. The tools to understand it would not exist for decades. But there it was, the first recorded observation of a relativistic jet captured on a glass photographic plate more than a century ago, waiting patiently for physics to catch up with it. We now know that the M87 jet extends for roughly 5,000 light-years. 5,000. If you could stand at the edge of the disk in the glowing inner ring where the temperature reaches into the millions of Kelvin, and if you could somehow watch the jet in real time, which you cannot, because the jet moves at nearly the speed of light and nothing you could observe would arrive in any kind of sensible order. You would be watching matter and energy being flung a distance roughly equal to 50 times the width of the Milky Way's stellar disk. And it does not wander, it does not disperse into a wide cone of radiation. It remains focused, collimated, coherent across all of those thousands of light years, like a beam from the most powerful and patient flashlight ever conceived. But why? Why does this happen at all, and why from the poles specifically? The answer begins with something we established earlier, but let's return to it from a slightly different angle because it becomes crucial here. The accretion disk spins. Of course it spins. That is the whole point of everything we have been talking about, the reason the disk exists in the first place. And as it spins, it drags something along with it. Not just the gas and the plasma, not just the particles and the ions and the electrons, it drags the magnetic field. Magnetic fields are threaded through nearly all astrophysical plasma. They do not come from nowhere. They are amplified, wound, shaped, and sustained by the motion of the conducting gas itself, the same ionized material that the magneto-rotational instability turns into a turbulent, viscous fluid. And as the inner disk spins faster than the outer disk, which it does because orbital speed increases as you fall inward toward any massive object, the same way a skater spins faster when she pulls her arms in, the same fundamental relationship between radius and velocity. The magnetic field lines that thread the disk get wound up. They get twisted. Spiral by spiral, turn by turn, the rotation of the disk wraps the magnetic field around the rotation axis, piling up coil upon coil of field line like thread being wound onto a bobbin. And coiled magnetic fields store energy. A lot of it. The magnetic field of the inner disk, wound tight and compressed, becomes an enormous reservoir of energy, not thermal energy, not the kinetic energy of individual particles moving randomly in all directions, but organized, structured, directional energy stored in the geometry of the field lines themselves. And that organized energy wants to go somewhere. Along the disk in the equatorial plane, it mostly goes into turbulence and viscosity. The magneto-rotational instability at work, the tangled field lines generating the effective friction that allows the disk to drain. But along the poles, where there is no disk, where there is no centrifugal barrier, where the field lines emerge from the wrapping and thread outward in the only direction that is genuinely open, something different happens. The field lines are not tangled and turbulent up there. They are ordered. They run in tight parallel spirals along the rotation axis, and they act like a guide wire for anything that gets caught up in them. Plasma that finds itself near the base of that polar magnetic funnel, heated, compressed, energized by proximity to the tremendous gravitational and magnetic forces concentrated near the black hole, gets accelerated along those field lines. The acceleration is both magnetic and centrifugal, the plasma being flung outward and upward the way a stone is flung from a rotating sling. And because the polar funnel is the one open direction, and because the field lines provide a coherent channel rather than a chaotic tangle, the outflowing plasma remains focused. It does not spread out, it stays in the beam. And it accelerates, steadily and continuously, reaching speeds that approach, very, very closely, the speed of light. This is the rough description of a process that two physicists, Roger Blanford and Roman Zanayak, worked out in extraordinary mathematical detail in 1977. Their paper described a mechanism by which a spinning black hole, a Kerr black hole, in the language of general relativity, named for the physicist Roy Kerr, who derived the mathematical description of rotating black holes in 1963, could transfer some of its own rotational energy into the magnetic field threading the region just outside its event horizon, and from there into the jets. Not the disk's energy. Not the energy of the infalling material. The rotational energy of the black hole itself. Think about what that means and take a breath with it, because it is a remarkable thing. A black hole has angular momentum. It spins. Not its surface. It has no surface in the ordinary sense, but its space-time. The region immediately outside a spinning black hole is not still. It is dragged. The very fabric of space-time is pulled into rotation by the mass spinning inside it, in a region called the ergosphere. This is not an optional effect, not a small correction. It is a fundamental consequence of Einstein's general theory of relativity, confirmed repeatedly by observation and experiment. In the ergosphere, nothing can remain at rest. The space-time itself rotates, and anything inside it is forced to rotate along with it, regardless of what forces might be applied. Even light, moving in the direction opposite to the spin, is carried around by the dragging of space. What Blandford and Zanijek showed is that magnetic field lines threading the ergosphere are also twisted by this dragging of space-time. They are forced to rotate with the black hole. And rotating magnetic field lines carry energy, electromagnetic energy, the same fundamental relationship between spinning conductors and generated fields that underlies electric generators. The black hole acts in a precise and mathematical sense as a kind of cosmic generator. The spinning space-time drives a current. The current flows along the field lines. The energy propagates outward along the polar funnel, and the jet is powered ultimately by the spin of the black hole itself. The black hole pays for its own jet. There is something almost quietly wonderful about that if you are still awake enough to appreciate it. Here is an object famous for never letting anything escape. Famous, in popular imagination, for being the ultimate destroyer, the perfect trap. And yet it is also, in exactly the right conditions, one of the most prodigal sources of energy in the universe. Not from inside, not from beyond the event horizon, but from the space-time just outside it, from the geometry of its own rotation, from the wringing out of spin energy by magnetic fields threaded through a region where gravity and momentum and electromagnetism are all conspiring together at the highest energies nature can produce. The spinning black hole gives away its spin to make the jet. Slowly, over time, the black hole loses angular momentum to the magnetic field and the jet. It does not stop spinning suddenly. This is a gradual process, and for a black hole of several billion solar masses, the timescale involved is almost unimaginably long. But it happens. The jet is not free energy. Nothing is free. The bill is paid by the spin, and the currency is time. Now, alongside the Blandford-Zanijek process, there is a companion mechanism described by Blandford and another physicist, Mitchell Payne, in 1982. The Blandford-Payne process does not draw on the black hole's own spin. Instead, it draws on the rotation of the disk itself, the same orbital motion that keeps matter in its spiral dance above the equatorial plane. Magnetic field lines threading the disk, not the ergosphere, but the disk material itself, are also wound up by the differential rotation, and plasma attached to those lines can be flung outward centrifugally along the field lines if the geometry is right. If the field lines are inclined at the correct angle to the disk plane, material riding them will flow outward and upward rather than inward and downward, launching it away from the disk along the magnetic structure. In practice, real astrophysical jets are probably driven by some combination of both processes. The Blandford-Zanijek mechanism extracts spin energy from the black hole for jets from spinning Kerr black holes. The Blandford-Payne mechanism extracts energy from the orbital motion of the disk itself. Both processes use magnetic fields as the transmission system. Both direct the energy along the polar axis. And both produce the same fundamental outcome, a focused beam of accelerated plasma threading outward through the one direction in the system that is not blocked by the centrifugal barrier. What can't go sideways goes up, and what goes up, in this case, goes up at nearly the speed of light for 5,000 light-years and beyond. There is one more thing to say about these jets before we move on, and it is one of the stranger pieces of observational physics in all of astrophysics, and one of the most satisfying to have explained. When astronomers measure the motion of jet material, and they can do this with very precise radio interferometry, tracking bright knots of plasma in the jet over months and years, they sometimes find that the apparent speed of the jet material is faster than light, not close to the speed of light, faster, several times the speed of light in some measurements. This is obviously impossible, or at least it seems impossible. Nothing can travel faster than light. This is one of the bedrock principles of special relativity, tested and confirmed to extraordinary precision across more than a century of experiment. So, what is happening? The answer is a geometrical illusion, and understanding it requires only a little careful thought. Imagine a jet that is not pointed directly away from us, but instead pointed at a small angle toward us, so that the jet material is moving not straight up out of the screen, but diagonally toward you, at some shallow angle. Now imagine the jet emits two pulses of light, one at the beginning of a certain interval and one at the end of it. The first pulse is emitted from a certain point. The second pulse is emitted from a point much closer to us because the jet has been moving toward us throughout the interval. The second pulse, because it is emitted from closer, has a shorter distance to travel to reach our telescope. It arrives sooner than it would if the jet had been stationary, so the arrival times of the two pulses are much closer together than the actual emission times were. When we try to reconstruct how fast the jet is moving by measuring how far it appears to have moved between the arrival of those two pulses, we divide what looks like a large displacement by what looks like a short time, and we get an apparent velocity that is larger than the real velocity. When the jet is pointed nearly straight at us, and some jets are because the universe arranges things in every orientation, this illusion can be extreme. The mathematics works out so that if the real velocity is close to the speed of light and the angle to the line of sight is small, the apparent velocity can be several times the speed of light, 5 times, 10 times in extreme cases, faster than light to any observer who does not know the geometry. This effect is called superluminal motion, and it has been observed in the M87 jet and in many other relativistic jets across the universe. It is not a violation of special relativity. It is a consequence of the finite speed of light combined with a very fast, nearly aligned source. Once you know the mechanism, you can actually use it to learn things about the jet. The apparent speed, combined with measurements of the intrinsic brightness and the Doppler shift, lets astronomers reconstruct the actual speed and the angle to the line of sight. The illusion, understood, becomes a tool. And what those tools tell us, in the case of the M87 jet and jets like it, is that the real speed is genuinely very close to the speed of light, not appearing to be, actually being. Material fired from the poles of the accretion disk around M87 star is moving at speeds of roughly 99.9% of c, the speed at which the universe's speedometer runs out, the speed that light itself travels in a vacuum and that nothing with mass can ever quite reach. The disk sits in the equatorial plane, blazing with friction and magnetic turbulence, converting angular momentum into radiated energy. The jet fires from the poles, channeling a fraction of that energy in a focused beam at nearly the maximum speed the universe allows. They are not two separate phenomena. They are the equatorial and polar expressions of the same situation, the same spinning infalling system, the same conservation law. The disk is what the angular momentum produces at the sides. The jet is what the same angular momentum produces at the top and bottom. The shape of the one explains the existence of the other. If you followed all of that, and even if you only caught pieces of it, and that is completely fine. There is no examination in the morning, I promise. You have now understood something that took the full weight of 20th century astrophysics several decades to work out. The jet is not an add-on. It is not a separate story. It is what the other side of the conservation law looks like when you tilt your head 90 degrees and look along the spin axis. And now let's step back from M87 star for a moment. Let's stay with black holes but shift the frame, because in May of 2022, 3 years after that first astonishing image of M87 star's glowing disk and shadow, the Event Horizon Telescope collaboration released a second image. And this one was different in a way that matters deeply to the whole story we have been telling tonight. This second image was Sagittarius A-star, the black hole at the center of our own galaxy, not 55 million light-years away, 27,000 light-years away, not 6.5 billion times the mass of the Sun, 4.3 million times the mass of the Sun, 1,500 times less massive than M87 star, and roughly 2,000 times closer to us. The image looks, at first glance, almost identical to the M87 star image from 3 years earlier. A glowing ring, a dark central shadow. The photon ring surrounding the silhouette of the event horizon, painted by light bending around the black hole's gravity on its way to the telescope array spread across the Earth's surface. The shadow of A-star A-star is approximately 52 micro-arcseconds across, compared to approximately 42 micro-arcseconds for M87 star, slightly larger in apparent angular size, even though the black hole itself is vastly smaller, simply because it is so much closer to us. But here is what made this second image more than just a confirmation, more than just a box ticked in the catalogue of photographic achievements. It was the same shape, the same glowing ring with a dark center, the same physical structure, an accretion disk and a shadow appearing around an object 1,500 times less massive and 2,000 times closer, embedded in a completely different galactic environment with a completely different history, existing at the center of a spiral galaxy rather than a giant elliptical one. The same shape, different mass, different distance, different galaxy type, different age, different surrounding environment, different feeding rate, different jet activity. And yet when the Event Horizon Telescope looked, it found the same geometry, produced by the same mechanism, following the same physical law. This is the power of a conservation law. It doesn't care about context. It doesn't negotiate with the specific history of any particular object or system. Angular momentum is conserved, energy radiates away, and the result is a disk. Every time, around a black hole containing the mass of 4 million suns, orbited by a thin ring of glowing plasma 27,000 light-years from where you are lying right now, tonight. Around a black hole containing the mass of 6.5 billion suns, 55 million light-years away in the core of a giant galaxy that is, in astronomical terms, almost unimaginably distant. The same shape, the same shadow, the same bright asymmetry on the approaching side, the same relativistic Doppler beaming, painting one side of the ring brighter than the other because that side is rotating toward the telescope, the light compressed and brightened by the motion. One law, a scale range of 1,500 to 1 in mass. The same answer. That Sagittarius A-star was harder to image than M87 star, incidentally. Not because it is farther away, is much closer, but because it is smaller in physical size and the gas around it orbits faster. Orbital period close to SGR A-star is measured in minutes, not days. Patches of gas that are brighter or dimmer change on timescales that are short compared to the hours needed to collect the data for a single image. It is as if you were trying to photograph a bonfire while the flames were dancing in the wind versus photographing a steady candle. The Event Horizon Telescope collaboration had to develop new techniques to combine data from multiple nights and average out the variability, producing what might be thought of as a kind of composite snapshot of a rapidly flickering source. The fact that they succeeded, that the image came through coherent and recognizable and carrying exactly the structure that theory had predicted, is itself a testament to how thoroughly understood the underlying physics is. The accretion disk around Sagittarius A-star was expected to look like that. The shadow was expected to be roughly that size. The ring was expected to be brighter on the side, approaching us. All of these things had been calculated in detail years before the image was taken. The image confirmed them. Theory and observation, separated by 27,000 light-years of space, finding each other exactly where each predicted the other would be. That is what a good physical law looks like. But we are not done with scales yet, because so far we have been talking about black holes, the most extreme objects in the known universe, the most concentrated, the most dramatic, the places where gravity reaches its maximum intensity and space-time curves so strongly that the geometry itself becomes the dominant feature of the physics. We have been talking about structures built around singularities, about accretion disks reaching temperatures of millions of Kelvin, about jets that travel 5,000 light-years, about shadows cast by the bending of light around the deepest gravitational wells in existence. And you might be forgiven for thinking that what we have been describing is something rare, something exotic, something that only happens in the most extreme conditions, under the most unusual circumstances, requiring the very specific combination of a supermassive black hole and infalling gas and magnetic fields of almost incomprehensible strength. But the disk is not exotic. The disk is mundane. The disk is everywhere. The disk is, in a very specific sense, the default shape that the universe builds whenever it has the right ingredients. And the right ingredients are not rare at all. They are gas or solid particles, gravity, and a little bit of spin. That's it. Those three ingredients appear together constantly at scale after scale after scale across the cosmos, and every time they do, the same conservation law runs and the same shape appears. The next scale down from black hole accretion disks is something you might have heard of in a different context entirely, something that is, in its own quiet way, just as beautiful and just as direct a demonstration of the conservation of angular momentum as anything we have described tonight. It's a protoplanetary disk, a spinning flat cloud of gas and dust surrounding a newborn star. And in 2014, an observatory called ALMA, the Atacama Large Millimeter Array, a collection of 66 radio dishes arranged across the high desert of northern Chile at an altitude of more than 5,000 meters, took an image of one of them that stopped the scientific community in its tracks. The star is called HL Tauri. It sits about 450 light-years from Earth in the constellation Taurus. It is very young as stars go, roughly 1 million years old, which in stellar terms is essentially a newborn, a system that formed while the ancestors of our ancestors were already walking upright on a very different Earth. HL Tauri is surrounded by a disk of gas and dust, the leftover material from the collapse of the molecular cloud that formed the star, still flattening and settling and beginning to organize itself into whatever planetary system may eventually emerge there. And the ALMA image of this disk was extraordinary, not because it showed a disk. Astronomers had known disks existed around young stars for decades, but because of what it showed inside the disk, concentric bright rings alternating with dark gaps, not one ring, not two, multiple rings clearly separated, the gaps between them darker than the surrounding material, as though something had swept those regions clean, had gathered up the material in those lanes and concentrated it, or removed it. Those gaps are almost certainly the footprints of planets in the process of forming. A planet clearing its orbital lane, sweeping up or scattering the material that would otherwise fill that gap, leaving a dark band in the disk as a signature of its presence. And HL Tauri is so young, 1 million years old, that the discovery forced a revision in thinking about how quickly planetary formation can begin. Planets were not supposed to be forming yet in a system that young, according to the models that existed before that image. The image said otherwise, but what we want to notice tonight is not specifically the planets. It is the disk itself, that thin, flat, spinning structure around a star, only about twice the age of the oldest mountains on Earth, built by the same mechanism that built the disk around M87 star and the disk around Sagittarius A-star, a cloud of gas and dust fell inward under gravity. It had net angular momentum, a small statistical excess of spin from the tidal torques between the different parts of the cloud as it contracted, and that spin could not be destroyed, it could only be redistributed. So the cloud flattened. The poles collapsed first because there was no centrifugal barrier there. The equatorial material could not fall straight in. The conservation of angular momentum held it back, and the result was a disk, flat and rotating, the minimum energy shape for the angular momentum the system was carrying. A disk around a black hole of 6.5 billion solar masses. A disk around a black hole of 4.3 million solar masses. And now a disk around a star of perhaps a solar mass or two, so young it still glows in infrared light from the heat of its own formation. The same shape, the same law, the same two facts doing all the work. Energy radiating away, angular momentum staying put, the system settling into the lowest energy state consistent with its stubborn conserved spin. And if H.L. Tauri seems distant, 450 light-years is not exactly your backyard. Then let us come still closer. Let us come to a solar system you know very well, the one you live in. Our own solar system is flat. This is something easy to say and easy to overlook because we are inside it and we cannot step back far enough to see it whole from the outside. But if you could somehow travel far enough from the Sun and look back, what you would see is all 8 planets, from Mercury out to Neptune, orbiting in very nearly the same plane. Not exactly the same plane. There are small tilts, small deviations. No solar system is perfectly flat. But within about 7 degrees, all of them. Mercury, which has the largest deviation, is still only about 7 degrees off the main plane. The others are closer, most of them within a few degrees or less, and all of them orbit in the same direction as the Sun itself rotates. This is not a coincidence. This is the fossil signature of the disk. Our solar system is flat because it formed from a flat disk the same way H.L. Tauri is forming from a flat disk now. The same process, 4.5 billion years earlier, in this very neighborhood of the Milky Way. The Sun condensed at the center. The disk of gas and dust orbited around it. Over millions of years, the dust grains collided and stuck together, growing from grains to pebbles to boulders to planetesimals to the planetary bodies we know today, inheriting the orbital geometry of the disk they formed within. The disk is gone now, dissipated and consumed, and blown away by the young Sun's radiation. But the planets preserve its memory. The flatness of the solar system is the disk's obituary. And there is one more thing about our solar system that is worth sitting with, because it connects directly back to the transport of angular momentum that we talked about earlier. The process by which the inner disk gives its spin to the outer disk, how mass and angular momentum separate in the disk, inner material falling inward and outer material carrying spin outward. In our solar system, this process has left a striking signature that puzzled astronomers for a long time. The Sun contains more than 99.8% of the mass of the entire solar system. Everything else, all 8 planets, all the moons, all the asteroids, all the comets, all the dust, is less than 0.2% of the total mass. The Sun is dominant, overwhelmingly, in the mass budget. But in the angular momentum budget, the Sun has only about 0.3% of the total angular momentum of the solar system. Almost all of the spin, about 99.7% of it, is in the planets, particularly in the orbital motion of Jupiter and Saturn and the outer planets. This is the angular momentum problem of the Sun, and it is a famous puzzle in planetary science. If the Sun formed from a spinning disk and simply collapsed, While conserving angular momentum, it should be spinning far faster than it is. The angular momentum should be concentrated where the mass is, but it is not. The mass is in the Sun, the spin is in the planets. The resolution, of course, is disk physics. Angular momentum was transported outward during the formation of the solar system, exactly as disk theory predicts. Not perfectly, not completely, and the details of exactly how involve magnetic coupling between the young Sun and the disk, and various other mechanisms that are still being studied. But the broad picture is clear. The disk transported spin outward while letting mass flow inward. The Sun fell toward the center, and the planets got the spin. The same mechanism that allows accretion disks to drain, the outward transport of angular momentum while mass moves in, also shaped the angular momentum distribution of the very solar system we inhabit. You are living in the downstream consequence of angular momentum transport in a protoplanetary disk 4.5 billion years ago, and so we arrive at Saturn. If there is one place in the solar system where you can see the disk in all its patient, unhurried glory, where the physics we have been talking about all night becomes something you can almost hold in your hands, it is Saturn. It is the rings. Close your eyes for a moment, if they are not already closed. Picture Saturn as you have seen it in photographs. The pale golden sphere banded with faint cloud belts, and then those rings, those impossible perfect rings, spread out around its equator like something placed there deliberately, like a piece of jewelry. The rings of Saturn are approximately 280,000 kilometers across. To give that a scale that might mean something, 280,000 kilometers is more than 70% of the distance from the Earth to the Moon. They are vast. If you laid the rings flat across space between us and our Moon, they would nearly reach. And yet for all that width, all that lateral sprawl, those rings are, on average, about 10 meters thick. In some places, maybe tens of meters. But 10 meters is a reasonable middle number, so you have something that is 280,000 kilometers wide and 10 meters thick. Think about that ratio for a moment, because it is one of those numbers that does not fully land the first time you hear it. 280,000 kilometers divided by 10 meters. That is 28 billion to 1. The rings of Saturn are 28 billion times wider than they are thick. A sheet of paper is roughly 1/10 of a millimeter thick. A sheet of paper 1 meter wide has an aspect ratio of about 10,000 to 1. To match Saturn's rings, you would need a sheet of paper that is, proportionally, about 3 million times thinner than it already is. Or, put another way, if you scaled Saturn's rings down to the thickness of a single sheet of paper, that sheet of paper would be about 3 kilometers wide. They are, by any reasonable measure, one of the thinnest large structures in the known universe, and they formed by the same exact physics that built the protoplanetary disk around HL Tauri, the same physics threading through the accretion disk around M87T, the same physics that flattened our solar system into a plane. The story of why Saturn has rings rather than another moon, or rather, why it has rings here, in this particular zone, begins with the Roche limit. Édouard Roche was a French mathematician working in the mid-1800s, and he calculated something that is still, when you work it through, a little bit startling. He showed that if you bring a smaller body close enough to a larger one, the tidal forces, the difference in gravitational pull across the body, becomes stronger than the small body's own self-gravity. And when that happens, the small body cannot hold itself together. It gets pulled apart. Every planet has a Roche limit, a distance inside which material simply cannot accrete into a moon. Tidal forces win. Things that cross inside the Roche limit in a solid body will be slowly shredded. Things that form inside it in the first place, like orbiting debris like the material in Saturn's rings, never get the chance to pull themselves together into something larger. Saturn's main rings sit inside Saturn's Roche limit. The particles in those rings, and they range from tiny dust grains up to objects roughly the size of a house, cannot coalesce into a moon. Every time two particles come close and begin to feel a mutual gravitational attraction, Saturn's tidal field is stronger and it gently prevents the merger, so the particles keep orbiting, each one on its own path. The ring is frozen at the moment just before it becomes a moon, held there by the balance between self-gravity trying to build something and tidal gravity refusing to permit it. And the same physics that flattened the protoplanetary disk flattens the rings to that extraordinary thinness. The particles are constantly colliding, not violently usually, but in gentle, grazing contacts because their orbital velocities are so similar. And every collision that is not exactly in the orbital plane has a damping effect on the vertical component of motion. A particle bobbing slightly above or below the ring plane will, through enough gentle contacts, have that vertical motion bled away. But the orbital, in-plane angular momentum is preserved. Collisions do not destroy the total spin of the system, they redistribute it. And so, over time, the ring settles toward the flattest possible configuration, the one that has dissipated as much vertical motion as possible while holding on to as much orbital angular momentum as it can. Energy dissipates, angular momentum persists. The disk is the result. It is the same sentence we have been saying all night, and here it is, written in ice. More than 95% of Saturn's rings by mass is water ice. Not rock, not metal, water ice. Bright, reflective, frozen water. The rings are one of the brightest things in the solar system for their size, precisely because of this composition. And when we look at them, when we see that pale, flat shimmer around the planet, we are looking at the same angular momentum physics that operates around a supermassive black hole 6.5 billion times the mass of the Sun, playing out in ice and silence at a scale of a few 100,000 kilometers, the same shape, the same law, in ice around a gas giant, in the cold outer solar system. There is something in that if you let it sit. So we have followed the disk law from the singularity-adjacent environment of black holes through the birth of solar systems, and now to the rings of Saturn. Let us step back even further, much further. Let us talk about the largest structures we can see, galaxies. A galaxy, in its most common form, is a disk. Not all galaxies, it's worth saying. There are galaxies that are not disks. The elliptical galaxies, which look like smooth, featureless blobs of stars, football-shaped or spherical. We will come back to them. But the most visually iconic galaxies, the ones that appear in photographs and on posters, and that most people picture when they hear the word galaxy, the spirals, the grand sweeping pinwheels, those are disks. The Milky Way is a disk. Our galaxy, the one we live in, is approximately 100,000 light-years across. And how thick is it? The stellar disk, the main body where most of the stars are, is about 1,000 light-years thick. 100 to 1. Not as extreme as Saturn's rings, nowhere near as extreme, but still 100 times wider than it is thick. We are living inside a flattened disk of several 100 billion stars, and we are located about 26,000 light-years from the center, out in one of the spiral arms, orbiting the galactic center at a speed of about 220 kilometers per second. One trip around the galaxy, one galactic year, takes us about 225 million years. The last time Earth was at roughly this position in its galactic orbit, dinosaurs were just beginning to appear. The disk of the Milky Way, formed by the same process we have been describing, the early galaxy was a rotating cloud of gas and dark matter. It had net angular momentum. We will get to where that angular momentum came from in a few minutes. that cloud began to collapse under gravity. The collapse was free and fast along the spin axis because there was nothing preventing it. But in the equatorial plane, the centrifugal barrier held up the material. Slow collapse preserved angular momentum, settling into the lowest energy configuration, a rotating disk. Stars form in the disk. Gas collapses in the disk. The arms and bars and rings you see in spiral galaxies are all features of a rotating disk. Density waves rippling through it, compressions where gas piles up and stars ignite, the whole vast structure coherently rotating. Now, the elliptical galaxies, the round ones, the blob-shaped ones. Why didn't they flatten? Two reasons, and both of them are instructive precisely because they confirm the rule from the other side. First, a galaxy needs net angular momentum to flatten. If you have a system in which the orbits are arranged randomly, some stars going this way, some that way, orbits inclined at all angles, little or no preference for rotation, then the individual angular momenta tend to cancel each other out. There is no net spin axis to flatten along. The system stays pressure-supported, meaning the stars hold it up like the atoms in a gas, moving in all directions, and it remains roughly round or elongated rather than flattening into a disk. Second, even if there is some angular momentum, you need a way to dissipate energy. Gas can collide and radiate. Gas can lose energy as heat and light through collisions between atoms and molecules. Gas follows the rule. Energy escapes, angular momentum stays, disk forms. But stars are much harder to collide. In a system of only stars without much gas, the energy dissipation is very slow. The stars cannot shed their random motions efficiently. They stay hot, dynamically speaking, and the system remains puffy. Elliptical galaxies are thought to form largely through mergers of smaller galaxies. When two disk galaxies collide and merge, the coherent rotations can be scrambled. Stars from both galaxies end up on all kinds of orbits. The gas gets thrown around and either consumed in star formation or expelled. What remains after the merger has settled is a large system of stars with randomized orbits, and that is an elliptical galaxy. The ellipticals are, in a sense, the stirred ones. The disks are the ones that were never stirred, or were stirred gently enough that their spin survived intact. And this is the exception that proves the rule. Flattening, the formation of a disk, requires net angular momentum and a way to dissipate energy. Where both conditions are met, you get a disk. Where one or both are absent, you get something rounder, something puffier, something that retained its three-dimensionality because it couldn't shed the energy it needed to lose. The disk is not the universe's universal outcome. It is the universe's outcome when certain conditions are met. And those conditions, net spin, plus a way for energy to escape, are met so commonly and so thoroughly across such a range of scales that the disk feels universal. But it is not. It is the specific, inevitable result of two laws working together, and the ellipticals are there to remind you that when one law falls away, the shape changes. This brings us to a question we have parked until now, and it is a good one to settle in with before we drift towards sleep. Where did all the spinning come from? It seems almost too fundamental to ask. Everything spins. Planets spin, stars spin, black holes spin, galaxies spin. Even the gas clouds that eventually become all of these things are already spinning, already rotating slowly before they collapse. So why is there spin? The popular answer, and it is one you will find if you look, is something like, the Big Bang gave everything its spin. The universe started spinning and things have been spinning ever since. But this is not quite right, and it is worth a gentle correction, because the real answer is more interesting. On large scales, the universe as a whole does not seem to have a preferred rotation. When cosmologists look at the large-scale structure of the universe, the vast web of filaments and voids and galaxy clusters, they do not find a net rotation. There is no axis about which everything turns. The universe, at the largest scales we can measure, is not spinning in any meaningful sense. So the spin that shows up in individual objects, in galaxies, in solar systems, in accretion disks, did not come from some primordial cosmic rotation that was set at the Big Bang and passed down. It arises more locally than that. The mechanism is called tidal torque theory. In the early universe, the distribution of matter was not perfectly uniform. There were tiny fluctuations, regions slightly denser than average, regions slightly less dense, and those density fluctuations exerted gravitational tidal forces on each other. When a proto-galaxy, a region of gas and dark matter that would eventually collapse into a galaxy, was embedded in this lumpy gravitational environment, the tidal fields of neighboring density fluctuations pulled on different parts of it with slightly different strengths and directions. These differential gravitational pulls, these tides, gave the proto-galaxy a small net spin. Not a lot, just a gentle torque, a subtle preference for rotation in a particular direction. But enough. Enough to mean that when the cloud eventually collapsed, it had some angular momentum to conserve, and the conservation of that angular momentum and the dissipation of energy gave it a disk. Tidal torques are also why different galaxies spin in different directions. There is no universal handedness to galactic rotation. Some spiral galaxies rotate clockwise as we see them, some counterclockwise. The Andromeda galaxy rotates one way, other nearby galaxies rotate other ways. Each got its particular spin from the particular configuration of density fluctuations in its local region of the early universe. And the same process, scaled down by many orders of magnitude, gives spin to the gas clouds that collapse into individual stars and planetary systems. A molecular cloud collapsing to form a new star is embedded in a gravitational environment, surrounded by the mass of the galaxy, by neighboring clouds, by density fluctuations in the interstellar medium. Those environments impart gentle tidal torques. The cloud ends up with a small net rotation, and that rotation, preserved by angular momentum conservation and shaped by energy dissipation, builds the disk. So the spin does not come from some grand cosmic source handed down from the beginning. It is acquired locally, gently, through the differential pull of gravity on slightly lumpy matter. Tidal torques all the way down. And then once the spin is there, the physics we have spent this whole night discussing takes over. Angular momentum conservation holds it. Energy dissipation shapes it. The disk is the result. Let us now do something that I find quietly wonderful, and that I want to offer you as a last image to carry into sleep. Let us stand back and look at the whole range of scales across which this one law operates. At the smallest end of what we have discussed tonight, the individual particles in Saturn's rings, ice grains and house-sized boulders orbiting Saturn in a disk roughly 10 meters thick. The scale of the thickness, about 10 meters. The width of the rings, 280,000 kilometers. Step up from there to a protoplanetary disk, a young star like H.L. Tauri surrounded by a disk of gas and dust a few hundred astronomical units across. 1 astronomical unit is the distance from the Earth to the Sun, roughly 150 million kilometers. So the disk of H.L. Tauri is something like tens of billions of meters across, many orders of magnitude larger than Saturn's rings. Step up again. Our solar system. The invariable plane in which the planets orbit. Pluto, one of the most distant members, orbits at about 40 astronomical units from the Sun. The disk we inhabit is roughly 80 astronomical units in diameter, about 12 billion kilometers, or 12 times 10 to the 12th meters. Step up further. The Milky Way, 100,000 light-years across. 1 light-year is about 9.5 times 10 to the 15th meters. The Milky Way is therefore roughly 10 to the 21st meters in diameter. And then up again, the accretion disk of M87 Sagittarius, whose glowing ring the Event Horizon Telescope captured in 2019. The Schwarzschild radius of M87 Sagittarius is enormous. For a black hole of 6.5 billion solar masses, the event horizon is roughly 20 billion kilometers across. The disk extends much further than that. Across these scales, from 10 meters to something like 10 to the 21st meters, the same geometry applies. The same law, the same competition between energy radiating away and angular momentum stubbornly staying. 20 orders of magnitude, that is a 1 followed by 20 zeros. If you tried to count from 1 to 10 to the 20th, and you counted one number per second without stopping, it would take you over 3 trillion years. The current age of the universe is about 14 billion years. And the same mathematical relationship, L equals m times v times r, rotational symmetry, Noether's theorem, the minimum energy configuration for a conserved quantity, governs all of it. There is nothing else in physics quite like this. There are other conservation laws, other fundamental principles, but very few that write themselves so clearly across such an enormous range of scale with such recognizable geometry. The disk is the universe's visible signature of angular momentum conservation. Every time you see that shape, whether it is Saturn's rings caught in a photograph, or a spiral galaxy in a deep field image, or the glowing ring around M87 photographed by the Event Horizon Telescope, you are seeing the same thing. The same law, made visible in a different medium, at a different scale, but expressing the same underlying truth. The universe does not know that it is making a pattern. It is not trying to build the same shape over and over. It is simply following rules, the rules of how angular momentum and energy behave, and those rules applied to matter under gravity, with almost any initial conditions that include some net rotation, produce a disk every single time. The disk is not a choice, it is not a preference, it is the only stable solution to the constraints, and you are embedded in one. Right now, wherever you are listening from, you are orbiting the center of a galaxy that is itself a disk. The planet you are lying on formed from a disk. The sun at the center of your solar system burned its first hydrogen inside the remnant of a disk. The heavy elements in your body and the calcium in your bones, the iron in your blood, the oxygen in the air you are breathing, were forged in stars that formed in disks and scattered back into the galaxy when those stars died, to be gathered up again in new disks to form new solar systems, including this one. You are, in the most literal sense, the downstream product of angular momentum conservation playing out across billions of years and dozens of generations of stars. The spinning that began as a gentle tidal talk in a cloud of gas 4.5 billion years ago, that built the disk that transported angular momentum outward and let mass fall inward, that ignited the sun, that built the planets from the remaining material in the disk's outer reaches. That spinning is still happening. Earth is still spinning. You are spinning with it. About 800 miles per hour at the equator, though you cannot feel it. And the whole solar system is spinning around the galactic center at 220 kilometers per second. And the Milky Way itself is moving through space, pulled by the gravity of the local group of galaxies. All that motion, all that inherited spin. And at every scale where that spin encountered gravity and gas and time and the slow, irreversible escape of energy as heat and light, the same shape formed, not because the universe prefers it, because it is the only shape you can make when you are not allowed to lose your spin, but you are allowed to lose your energy. The disk is the shape of conservation itself. I want to leave you with one more thing, and it is something small and quiet. The next time you see a photograph of Saturn, and perhaps you have seen it many times, that golden planet with its extraordinary rings, look at those rings differently now. They are not decoration. They are not accident. They are the same law that makes a black hole's accretion disk glow in X-rays and fire jets 5,000 light-years into space. The same law that built the concentric rings in the ALMA image of HL Tauri, where a planetary system is assembling itself right now around a star just 1 million years old, which is barely an infant by cosmic standards. The same law that spun the Milky Way flat so that when you look at the night sky from a dark place and see that faint river of light arching overhead, you are looking along the plane of the disk at the accumulated glow of hundreds of billions of stars all orbiting in roughly the same direction, the same law. Everywhere you look, physics at its best does something strange and calming at the same time. It takes things that seem unrelated, a gas giant's rings, a newborn star's disk, a supermassive black hole's glowing halo, a galaxy's spiral arms, and shows you that they are the same thing. That beneath all the variety and apparent chaos of the universe, there are a small number of deep rules, and those rules, when followed faithfully, build the same shapes at every scale. The disk is one of those shapes, and now you know why. When the Event Horizon Telescope looked at M80 Sagittarius 55 million light-years away and captured that orange ring of light around a dark center, it was doing something that would have seemed like pure fantasy to scientists just a few decades earlier. It was making the invisible visible. It was photographing a shadow cast by the curved space-time around a black hole 6.5 billion times the mass of the Sun. And what it found when the images came in on the 10th of April 2019 was a ring, a disk, the same shape. Not because anyone expected the universe to be tidy, not because physics was supposed to be simple, but because angular momentum is conserved and energy radiates away, and those two facts together, given enough time and enough gravity, always build the same thing. When they looked at Sagittarius A 3 years later, in May of 2022, and captured the shadow of the black hole at the center of our own galaxy, 4.3 million solar masses, 27,000 light-years from where you are lying right now, they found the same shape again. A ring, a shadow, a disk. Two black holes, different galaxies. Mass ratio of 1500 to 1. Same shape. The law does not vary with distance. It does not vary with mass. It does not vary with time. It is written into the structure of the universe at a level so deep that it expresses itself identically whether the stage is a handful of ice particles orbiting Saturn or a billion tons of superheated plasma spiraling toward a singularity. And I find that somehow enormously comforting, not because it makes the universe small or simple, it doesn't. The universe is stranger and more vast than we can really hold in our minds, but because it means the universe is coherent, it is following rules, and we have, over the course of a few centuries of curious, persistent, often stubborn human thinking, figured out some of those rules. We followed the geometry of a black hole's shadow back to the conservation of angular momentum, back to Noether's theorem, back to the rotational symmetry of space itself. We started from a glowing ring photographed by a network of radio telescopes, and we traced the line all the way back to a mathematical truth about the symmetry of the laws of physics, and that line passes through Saturn's rings and HL Tauri and the Milky Way and everything in between. That is not a small thing. That is quietly one of the most remarkable things our species has ever done. You asked at the beginning of tonight why the universe keeps building the same shape. And the answer, in its simplest form, is this. Because space is rotationally symmetric, angular momentum is conserved, and energy is not. Those three facts together mean that any cloud of gas with even a tiny net spin collapsing under gravity, will shed its energy but not its spin, and the shape that results, the minimum energy state for a fixed amount of angular momentum, is a flat, rotating disk. Every time. At every scale. The disk is not the universe's preference. It is the universe's consequence. It is what the rules require. And the jet, the polar jet that fires from the one direction the centrifugal barrier leaves unguarded, the jet is not separate from the disk. It is the same solution, seen from a different angle. The disk is what happens in the equatorial plane. The jet is what happens at the poles. The same spin that forbids the plunge powers the escape. They are the equator and the poles of one answer to one law. You could see all of this in the photographs the Event Horizon Telescope took. The ring, the shadow, the brighter side rotating toward us. It is all there, in the light. The universe wrote its physics in a glowing disk around a black hole 55 million light-years away, and we built a telescope the size of the Earth to read it. And it said the same thing that keeps the planets in their plane, the same thing that gave Saturn its rings, the same thing that organized the Milky Way into a flat spiral, the same thing that built the disk is the same thing that tried to stop matter from falling, and that fired the jet when matter couldn't fall sideways, and so went up instead. One law, one shape, everywhere. That is the answer. You are carrying it with you into sleep now. It will be there when you wake up. The rings of Saturn will still be 280,000 kilometers wide and 10 meters thick. H.L. Tauri will still be building planets in its disk. M87 will still be burning through mass at the rate that makes its accretion disk outshine the galaxy around it. Sagittarius A will still be sitting at the center of the Milky Way, patient and massive and ringed by its own glowing disk of infalling gas. And you will still be here, in a solar system that is itself the fossil of a protoplanetary disk on a planet made of materials that passed through several generations of stellar disks before becoming the world you know, spinning at 800 miles per hour on a planet orbiting a star at 67,000 miles per hour in a galaxy rotating at 220 kilometers per second. All that spinning, all of it inherited, all of it conserved. You are not separate from any of it. You are made of the same spinning fields, the same conserved angular momentum, the same atoms that once lived in a disk somewhere and were shaped by the same law we have been talking about all night. Back at the very beginning, I asked you why the universe keeps building the same shape, and I promised you that the answer was in one photograph and one law. The photograph was the Event Horizon Telescope's image of M87 in 2019, that glowing, asymmetric orange ring around a central shadow. A disk. The law was the conservation of angular momentum. L equals m times v times r, and it does not go away. The shape is the disk. And now you know exactly why. Wherever you are tonight, whatever corner of the world, whatever hour it is, whatever lamp is still on or window is still faintly light, I hope this felt like a long, slow walk through something real and strange and quietly beautiful. I hope some of it settled in, and I hope most of it was just the right kind of interesting to help you drift. If you enjoyed this slow journey and would like more nights like it, a gentle like and subscribe helps this sleepy little channel keep going. Small creators like me really do rely on your support to keep making these. And please leave a comment. Tell me where you're listening from tonight and what time it is in your corner of the world. I love knowing where these words reach. Stay as long as you like in Nightoria. Good night.